In the last lecture, we talked about reducibility of representations. We saw that reducibility came in two flavors, plain reducibility and something slightly more specific or something deeper, complete reducibility. Now, we also said in the end of the last lecture that for finite groups, the distinction really does not matter. We are going to explain that in this lecture at the beginning, and then we are going to go on to talk about several very important results. But before we do that, let us recall exactly what these concepts of reducibility, plain reducibility and complete reducibility, really mean. Recall that at the level of linear representations, an operator representation L on a vector space V is said to be reducible if there exists a non-trivial subspace V prime of capital V, which is invariant under the action of L of G for all small g belonging to capital G. So for all elements of the group, the action of the corresponding linear operator on any vector in the space V prime will only yield a vector in the space V prime. Now, at the level of matrix representations, as we had seen in the last lecture, if you were to choose your basis properly, that is, if you were to choose your basis so that the first lot of basis vectors would be all the basis vectors of V prime, and then you extend this with other vectors to form a basis of capital V, the matrix representation for each small g will have a completely zero block below the diagonal. Remember, we are just saying block triangular and not actually triangular. And that is a very important distinction. Let's contrast this with the notion of complete reducibility. An operator representation capital L on a vector space capital V is said to be completely reducible if capital V is a direct sum of two or more non-trivial subspaces, all of which are invariant under the action of Lg for all small g belonging to capital G. Note that the major distinction between this particular notion of reducibility, that is complete reducibility, and plain vanilla reducibility that we talked about earlier, is simply that when we were just defining a representation's reducibility, we demanded that there is a non-trivial subspace which is invariant, but we did not say anything about the complementary subspace, about the rest of the vectors. Here we are claiming that you can build up your vector space capital V with essentially smaller subspaces, each of which are actually invariant under all of the LGs as G runs over the entire group capital G. And a consequence of this is, if we were to talk about the corresponding matrix representation, then again with a proper choice of basis, the matrix representation will be block diagonal. Let me repeat a warning that I had given in the last lecture as well. While the matrix representation will be block triangular for a reducible representation or block diagonal for a completely reducible representation, if you choose your basis properly, very often you may have been forced to use an entirely different basis, and hence the representation matrices may not look either block triangular in the previous case or block diagonal in this case. So the whole point is, when you're looking at matrix representations, reducibility, either plain vanilla reducibility or complete reducibility, will be based on whether you can find such a basis where the block triangular or the block diagonal form emerges, or in other words, whether you can do a given similarity transformation on each and every one of the representation matrices so that the block triangular or block diagonal form is reached. Now, while we are trying to be very precise in carefully distinguishing between reducibility on the one hand and complete reducibility on the other, as it so happens, the distinction is primarily academic, at least for a large class of groups. And the reason behind that lies in a theorem that we are going to talk about now. This theorem simply states that a unitary reducible representation of a group on an inner product space must be completely reducible. So if you have a unitary representation of a group, of course, for a representation to qualify as a unitary representation, the underlying vector space must have an inner product defined on it. And if you have such a representation which is reducible, then it is automatically completely reducible. To see why, let us just consider this situation. L is a unitary reducible representation on an inner product space V. And because L is reducible, there must be an invariant subspace capital V1 of capital V, which is invariant under the action of capital L. This capital V1 is invariant under the action of capital L of G for each and every small g in capital G. Now what we do is we define an orthogonal complement of V1, call it V1 perpendicular, by the following definition. V1 perpendicular is a set of all vectors small v2 such that v2, v1 is 0. The inner product of v2 with v1 vanishes whenever v1 is a vector in capital V1. So in other words, capital V1 perpendicular is a set of all vectors which are orthogonal to every vector in capital V of 1. Now what you can easily check is that this V1 perpendicular, which we can also call V2 now, is a subspace of capital V. As we will now show, this vector space V2 is also invariant under L of G for all small g belonging to capital G. The way we do that is the following. We start with any vector small v2 in capital V of 2. Of course, this means this small v2 has a property that it is orthogonal to each and every vector in capital V1. And what we want to show now is that L of G v2 is also in capital V2. Now, for any V1 belonging to capital V1, let us form this inner product of V1 with L of G V2. Now, because of the definition of the adjoint, you can easily see that this is the same as L of G's adjoint acting on V1, inner product of that with V2. This, of course, is nothing but the definition of the adjoint operator. But because our representation is unitary, LG dagger is the same as LG inverse. And that exactly is what defines a unitary representation. But LG inverse, of course, is L of G inverse. So what we have is that the inner product we started out with, the inner product of V1 with LG V2, is the same as the inner product between LG inverse V1 and V2. Now note that LG inverse V1 is one of the group vectors in capital V1 because G inverse is in capital G, so LG inverse is an operator in the representation, and capital V1 is invariant under all the operators in the representation L, which means it's also invariant under L of G inverse. Hence, L of G inverse acting on V1 is a vector in capital V1. And thus, by our definition of capital V2, small v2 is orthogonal to it. So this inner product is 0. So what does this mean? It means if you start with a vector in capital V2, namely small v2, apply L of G on it, the resulting vector has to be orthogonal to any vector small v1 in capital V1. Hence LGV2 is in capital V2, and so V2 is invariant under L. Now, one result follows very trivially from linear algebra that the original space capital V is actually a direct sum, or is really isomorphic to a direct sum of the spaces V1 and V2. Let me warn you once again here, when I say isomorphic in this context, I mean isomorphic as linear vector spaces. Of course, not isomorphic merely as groups. But since capital V is isomorphic to V1 direct sum with V2, and both V1 and V2, as we have just seen, are invariant under the action of all of the L of G's, it follows that we have been able to show that our space is a direct sum of invariant subspaces, and so L is completely reducible. This concludes our proof. Now, what is the consequence of that as far as our distinction between reducibility and complete reducibility is concerned? Note that what we have shown here is that if you have a unitary representation which is reducible, then it has to be completely reducible. Now recall a result that we had actually derived earlier, which is for a finite group, each and every representation is equivalent to a unitary representation. And what this means is that for a finite group, each and every reducible representation is completely reducible. It may not be reduced. You may have chosen a basis in which the reducibility does not show up, at least at the matrix level. But if you can reduce it, that means if you can see your matrices in a block triangular form, then just by a change of basis, it is guaranteed that you will be able to get them in a block diagonal form. So for finite groups, reducibility is the same as complete reducibility. And let me just remind you that this result also extends not just to finite groups, but infinite groups of a special kind called compact groups. Once again, we will talk about compact groups in detail later. This is just to remind you that the result not only works for finite groups, it also works for a bigger class. As we have seen, reducibility is directly connected to the notion of direct sum of representations. This, of course, is a way of building bigger representations out of smaller ones. Now, there is another important way in which bigger representations can be built out of smaller ones. It's a different and very, very important approach, simply because this is something which recurs over and over again in physical applications. This is a direct product of representations. And essentially what this is about is the following. If you have a system which is composed of many subsystems, and each part of the subsystem responds to a symmetry operation in a particular way, you can use those responses put together to figure out how the whole system is going to respond to a symmetry operation. And that exactly is what a direct product of representations tries to capture, especially in the situation where the individual subsystems are described by vector spaces of their own. This is of immense importance in many branches of physics and in quantum mechanics in particular, because in quantum mechanics, multi-component systems are described by vector spaces which are direct product vector spaces of their components. And the most common application of direct product representations perhaps comes from this particular aspect of quantum mechanics. Let us now turn to the formal definition of the direct product of two individual representations, L alpha and L beta, which are acting respectively on vector spaces V alpha and V beta. In order to define this representation, what we need to do is we need to figure out what operator corresponds to every single element small g of a group capital G. This is how it's defined. L alpha O times beta is this representation which maps a group element small g to an operator L alpha O times beta of small g. And this operator is defined by its action on the direct product vector space of V alpha and V beta. Now, the way in which we define this action is, we first define the action on a specific kind of vector, which is a direct product of vectors 1 As you all know, the direct product vector spaces contains many vectors which are not direct product of individual vectors from vector spaces. While this may not be exactly appropriate here, let me remind you that one of the biggest issues with modern quantum mechanics, that of entanglement, is exactly related to this particular point, that a direct product vector space has in general many vectors which are not direct products of individual vectors from vector spaces. So how do we define the action of L alpha O times beta of G on a general vector in the direct product vector space? Well, that's straightforward. All we do is we define this action by extending the above action using linearity. That is, we know that all vectors in the direct product space are linear combinations of vectors which are direct products, and we just insist that L alpha O times beta of G is a linear operator. So what it does on a linear combination of, since all vectors in a direct product space is a linear combination of direct product of two vectors, one from B alpha and another from V beta respectively, a very obvious choice of basis for the direct product space is as follows. We start with the situation that V alpha and V beta are D alpha and D beta dimensional vector spaces respectively, and we have two sets of ordered bases of V alpha and V beta, namely the set, or actually the tuple, because we are talking of ordered bases, E1 alpha, E2 alpha up to ED alpha alpha, that's the ordered basis for V alpha, and E1 beta, E2 beta up to ED beta beta, that's the ordered basis for V beta. Given this, a basis for the direct product space can be formed simply by taking direct products of individual basis vectors taken pairwise. That is, if you form the collection of d alpha times d beta vectors, which are ei alpha direct product with ej beta, where I runs all over 1, 2, 3 up to d alpha and j runs all over from 1, 2, 3 up to d beta, this forms an ordered basis for the direct product space V alpha O times V beta. Now, given this choice of basis, we can easily figure out what a corresponding matrix representation for L alpha O times beta is going to be, simply by making L alpha O times beta of G act on EI alpha O times EJ beta. Now, what happens when L alpha O times beta G acts on EI alpha O times EJ beta is clear from the definition of the direct product representation. L alpha G, which of course is a representation on V alpha, acts on EI alpha, and L beta G acts on EJ beta, and the resulting vector, the output of L alpha O times beta G acting on EI alpha O times EJ beta, is simply the direct product of these two vectors. Now, since L alpha G has an equivalent matrix, and so does L beta G, we can use that to figure out what happens to the basis vector EI alpha O times EJ beta of the direct product space under the action of L alpha O times beta G. And this is all that really happens. Just going back a bit, note that L alpha G EI alpha is going to be expressible as a sum from K running from 1 to D alpha of dk I alpha G ek alpha, and L beta G EJ beta will be equal to L running from 1 to D beta dLj beta G EL beta. And since the direct product between vectors has this linearity property, this immediately can be rewritten in the form sum over K going from 1 to D alpha and L going from 1 to D beta of dk I alpha G dLj beta G times ek alpha O times EL beta. Thus, the direct product matrix representation turns out to be dkl, ij element of alpha cross beta G is dki alpha G times dLj beta G. So basically you multiply the elements of the two matrices to find the corresponding matrix element for the direct product. Please note that KL, IJ on the left of the equation here basically are not 4 indices, there are really 2 indices. KL, the pair, is one index for the direct product matrix. IJ, the pair, is another index for the direct product matrix. It is easy to see why the pair IJ behaves like a single index for the direct product matrix. After all, IJ denotes a single basis vector in the direct product vector space, namely the basis vector E alpha I O times E beta j. Since each basis vector is actually labeled by a pair of indices, a single index which stands for one basis vector here really translates to a pair of these indices. Of course, for the matrix representation, we need to order the basis vectors of the direct product space in a particular order, and the standard ordering we choose is basically what is called dictionary order. The first index takes dominance, so when that is bigger, you put that element afterwards, and for 2 elements where the first index is the same, you actually go by the second index. So basically, 1 1 comes before 1 2, 2 1 comes after that, and then you get 2 2. This of course is a case where d alpha and d beta, the dimensionalities of both vector spaces, is simply 2. If the dimensionalities were say 2 and 3 respectively, then you would have 1 1, 1 2, 1 3 in that order, and then you will get 2 1, 2 2, 2 3. This is the standard dictionary order in which we order the basis vectors so that we can get a definite matrix representation out of this. In order to make this process of forming the direct product matrix representation a bit clearer, let us take a look at a specific example. We will use an example of a representation that we already know, that of a two-dimensional representation of the group S3 that we had constructed in an earlier lecture, and form a direct product of that representation with itself. Of course, because we are taking a direct product of two-dimensional matrices, the resulting representation is 4-dimensional, so it will be given by 4x4 matrices. And the rule that we stated right now of finding out the matrix elements of the direct product matrix by multiplying individual matrix elements and ordering the paired matrix elements in dictionary order, that translates to a very, very simple rule for determining the direct product matrix, and that's what we are going to illustrate with this example. So this is the 2D representation of S3 that we had calculated in a previous lecture. The 6 elements E, A, B, C, D and F of the group S3 are represented by these 2x2 matrices, and we are now going to form D2 cross 2. That is, this is a 4-dimensional representation, let's call this D4, and D4 corresponding to the identity element D4E will be D2E direct product with D2E. So we want to determine the matrix here. In this case, of course, there is really nothing much to do, because we know that because we are talking about the identity, the corresponding D4 has to be the 4x4 identity matrix. But let's illustrate the procedure by which we would have calculated it if we had not known it already. So basically what we are going to do is take a direct product of the 2x2 identity matrix with itself, and the rule that we talked about so far translates to this simple procedure. Basically, you treat this as if each element of the matrix on the left is actually being multiplied by the matrix on the right. Here it's a bit difficult to say which one goes where, because after all the two matrices are identical, but as it will always be, because we are taking D2 with itself, D2's direct product with itself, so which means for every one of the things we are going to use the same matrix twice, but the basic idea is this one here is basically the one sitting on the left here, the 0 here is a 0 on the left hand matrix here, and so on, and this matrix which is on the right gets multiplied by each of the 4 elements. Of course, when you multiply this matrix by 1, you get the matrix 1 0 0 1. Here if you multiply it by 0, you get 0 0 0 0 and so on. And so this clearly translates to this 4x4 matrix, which of course is no big deal, it's just the identity matrix back, as it should be. A slightly more non-trivial thing, let's look at D4A. That's D2A, O times D2A. So you take the D2A matrix, form a direct product of it with itself. And once again, the rule is very simple. You take each of the 4 elements here and multiply them each by the matrix to form a 4 by 4 matrix. So you get minus 1 times this minus 1, 0, 0, 1 matrix, and 0 times this, 0 times this here, 1 times this here. And a very simple calculation will give you this particular form for the matrix. So we have found out the 4 by 4 representatives for the identity, which was rather simple, and for the element A, which also is rather simple. To see a slightly non-trivial example, let's form D2B O times D2B, that is D4 of B. And this again is simply a direct product of these two matrices. And by following the same rule, what you have is half times the second matrix sitting here, root 3 by 2 times the second matrix again, and root 3 by 2, this corner element, times the second matrix, minus half the lower corner element times the second matrix here. And when you multiply everything out, you get a rather imposing looking 4 by 4 matrix. Now notice that this particular matrix is not diagonal at all, unlike the previous two. Not only is it not diagonal, it's not even block diagonal. You can of course continue in this fashion to find out D4C, D4D and D4F. I will leave this as an exercise for you to work out. But the main thing is, as you can well realize from this one example, the 6 matrices that you get do not have a block diagonal structure at all. On the other hand, what we do know is that this particular representation happens to be reducible. How do we know that? Well, that is something which we are going to explain in the future lectures. We actually happen to know that this particular group S3 has only 2 one-dimensional and 1 two-dimensional irreducible representations. So of course this 4 by 4 representation that we have here has to be reducible. But what I would like to point out to you is that because we are choosing a basis which is already given to us, that is the standard or natural basis is a direct product space, the matrices that we are getting shows no sign of being block diagonal at all. We should be able to find a similarity transformation which is going to convert this particular matrix, not only this particular matrix, the one you see on your screen right now, but all the 6 4 by 4 matrices for the 6 group elements into an identical block diagonal form. But the important thing is finding out such a similarity transformation which will do this for each and every one of the matrices is not a very simple task. In fact, figuring out whether this can at all be done is not simple at all. Well, you don't really have to search for this similarity transformation in the dark. Group representation theory, what we are studying right now, actually gives you a great deal of help in finding out this reduction. And the help actually comes in form of a result which is so very important that even the most staid of textbooks written by English authors, for example, even they refer to this particular theorem as the great orthogonality theorem. In fact, not all authors call these theorems great. There have been books where these theorems have been called magnificent or wonderful. To be fair, these other nomenclatures are primarily those that you find in textbooks written by non-English speaking authors. The words magnificent and wonderful basically are the result of translations to English. So even if you leave the vagaries of translation aside, the fact that people are using such superlative adjectives here do show that this theorem is really powerful and important. What we are going to study next is not really these theorems directly. We will study 2 lemmas which pave the way towards the proof of the great orthogonality theorem. In fact, in a sense, these lemmas are actually much more important than the theorems themselves, simply because The particular theorem that we are referring to is just one result. These lemmas actually can be used to prove many other interesting results in group theory. These lemmas are named after Isai Schur, a Russian mathematician who did most of his work in Germany. Now, these lemmas are presented in many textbooks, especially physics textbooks which deal with group theory, as lemmas involving group representations, in particular matrix representations. In reality, they are actually lemmas which deal with linear algebra, and it so happens that their most common use is in group representation theory. Now, while most textbooks do specifically address the group representation aspect of these lemmas, in my opinion, that makes their statement and the proof a bit more cumbersome than it needs to be. The linear algebra version of the lemmas is actually much more elegant and in fact easier to understand. And once you understand the linear algebra version of Schur's lemmas, it's very easy to translate them to whatever language you need them in. In particular, it is very easy to translate the result into whatever is needed for group theory. So what we are going to do is we are going to state the lemmas and prove them in their original linear algebra version. In the next lecture, we are going to actually use these lemmas to prove very important results in group theory. In particular, we are going to use it at the very outset to prove the great orthogonality theorem. In order to state these lemmas in the language of linear algebra, we need to define an important concept first. This concept is that of an irreducible set of operators. Now, to understand what this is, let us realize that for any linear operator capital T acting on a vector space V, there are true subspaces which are always invariant under T. One of these subspaces is none other than the trivial subspace with just the null vector. Of course, a linear operator acting on null vector will always give you the null vector back. So this set is invariant under the action of T. And the other one is perhaps even more trivially invariant, that is the entire space capital V itself. Of course, if you take any vector small v in capital V and apply capital T on it, since capital T is a well-defined linear operator from V to V, the result will have to be in capital V. So capital V, of course, has to be invariant. So these are trivial subspaces. Now, a set of operators, T1, T2, and so on, is called an irreducible set of operators if these two trivial subspaces are the only subspaces that are invariant under each one of T1, T2, and so on. Note that if you just picked one linear operator, it would be easy to find non-trivial linear subspaces which are invariant under the action of that operator. Well, all you have to do is take a look at an eigenvector of the operator and apply T on it. Of course, you get back a multiple of the eigenvector. So, any space which is spanned by an eigenvector, or in case the eigenvalue is degenerate, spanned by the corresponding eigenvectors, will be invariant under the action of capital T. So, if you had just a single operator, it would hardly ever be irreducible. But if you have multiple operators, it is very possible that the only subspaces which are invariant under the action of each and every one of the set of operators happens to be just these two trivial subspaces. If this happens, then the set of operators is called an irreducible set of operators. So what exactly would a reducible set of operators be? Well, a set of operators would be reducible on a vector space V if there is a non-trivial subspace V1 which is neither the null subspace nor the whole space capital V, which is invariant under the action of all of these T1, T2, T3, Tn. And why is this an important concept for us in group theory? Well, the set of operators LG, when small g runs over the entire group capital G, for an irreducible representation L on a vector space V, form a set of irreducible operators on the space V. Now that's sort of trivial from the definition of an irreducible representation. Remember, if a representation is reducible, then there is a space V prime, a non-trivial subspace V prime, which is invariant under the action of all of the LGs. If it is irreducible, it just means no such non-trivial subspace exists. And that is exactly what is meant when you say the set LG as G runs over the entire group capital G is an irreducible set of operators. Of course, the reason why we bothered to define the concept of an irreducible set of operators is that it is in terms of them that the Schur's lemmas, which, as I have already stated, are central tools used in the discussion of irreducibility or otherwise of group representations, can be stated. There are two Schur's lemmas, and for the first lemma, what we need are two vector spaces V1 and V2 and two irreducible set of operators, irreducible set of n operators each on the two vector spaces. So Ti1 as I runs from 1, 2 all the way up to n, and Ti2, here again I runs all over from 1, 2 all the way to n. These give you two irreducible set of operators on these two vector spaces. And in addition, what you have is a map X between V1 to V2. And this X obeys this particular relation. If you apply X after you apply Ti1, that is, you apply the composite transformation X Ti1, the result is the same as the one that you will get if you were to apply X first and then apply Ti2. That is, you apply the composite operator Ti2x. And this will work for each and every value of I running from 1, 2 all the way up to n. It is very tempting to say at this stage that X commutes with the Ti's, but please note that the two Ti's on the two sides are actually two different operators. You have Ti1 which acts on the space V1 and Ti2 which acts on the space V2. So a correct term would not be to say that X commutes with the Ti's. A correct term would be to say X intertwines the two sets Ti1 and Ti2. Schur's lemma is a statement about such an intertwining operator. And the statement simply is that if such an intertwining operator exists, then this operator has to be either the null operator, that is an operator which maps every vector of V1 to the null vector of V2, or the other extreme, that is X inverse must exist. So there is nothing in between. X can either be the null operator or must be an invertible operator. So this is what lemma 1 says. Let me point out one thing at this stage. While we have labeled the two vector spaces V1 and V2, and this of course leaves open the possibility that these two vector spaces are distinct vector spaces, it's also quite possible that we are using this lemma in a situation where V1 and V2 both refer to the same vector space. Now, while the two spaces in lemma 1 could be the same space or two different spaces, the two spaces involved in the second lemma, the one which I am going to state now, are definitely the same vector space. So here we are talking about one vector space capital V and an irreducible set of operators Ti, I running from 1, 2, 3 all the way up to n, and we demand that there is an operator X from V to V which actually does commute with all the Ti's. So xTi is Tix for I running from 1 to n. And this, of course, is genuine commutation because the two ti's that you have on both sides of the equation are one and the same. So in this particular case, what the lemma says is that x must be a multiple of the identity operator. Of course, by looking at lemma 1, you would have immediately concluded that x must be either 0 or its inverse must exist. Let me point out that even the null operator here is a multiple of the identity operator, simply the identity operator multiplied by 0. So the case x equal to 0 is also covered by the statement that x is a multiple of the identity operator. What this second lemma says is that when v1 and v2 are the same space, then it's not enough that x be invertible. It has to be essentially the identity operator up to a multiple. Let us now turn to the proof of these two lemmas. In both cases, the proof essentially hinges on two specific subspaces associated with the map X. And these are very familiar subspaces from linear algebra, namely the kernel of X, ker X, and the image of X denoted by mx. Let me just remind you that the kernel of X is a set of all vectors in the domain capital V1 which maps onto the null vector of V2. And the image of X is nothing but the collection of all the vectors that you can get in V2 as a result of X acting on vectors in V1. Now, it is a very standard result in linear algebra, and it is very trivial to prove these results, so even if you don't know the results already, you can easily prove them yourselves, that both of these subsets of V1, the domain, and V2, the range, respectively, are actually subspaces. They are not just subsets, they are vector spaces in their own right. And what we are now going to prove is that these are also invariant subspaces under the action of all the TIs, our irreducible set of operators. Let us begin with the kernel of capital X. And what we want to show is that the kernel of X actually is an invariant subspace under the action of the operators Ti1. In order to show this, what we do is we pick a specific vector, let's say small k, from the kernel of X. And then ask what happens when you apply X, the operator, on Ti1k. Now, since xTi1, according to our conditions of the lemma, is the same as Ti2x, this is of course the same as Ti2x acting on k. But since k is in the kernel of X, X acting on the k is the null vector of V2, and Ti2, the linear operator acting on V2, acting on its null vector, must give me the null vector. So the result has to be 0, the null vector of V2. So what this proves is that for every vector small k in ker X, Ti1 acting on small k is also in ker X. So ker X is invariant under the action of Ti1, and this works for all the values of I from 1 to n. However, our supposition was the set Ti1 as I runs from 1 to n is an irreducible set of operators on V1. What that means is that all these operators cannot have simultaneous invariant subspaces except for the trivial subspaces. So we have only two choices. Ker X must be either the trivial subspace with the null vector alone, of course this null vector is the null vector of V1, or it must be the entire space V1. Now if ker X is V1, then what it simply means is that if you take any vector in V1, you apply capital X on this, you are going to end up with the null vector of V2, which is exactly the statement that capital X has to be the null map, the zero map. The other possibility, of course, is Ker X is simply the trivial subspace which contains the null vector of V1 alone, and it is a very simple result in linear algebra, and you have also seen a very similar result in the isomorphism theorems, that if this is the case, if the kernel happens to be just the null vector of V1, then X has to be a 1-to-1 map. So you have only two possibilities, either X is 0. If it is not 0, it has to be 1-to-1. Now let us continue on the same line of argument with the image of X. Now if a vector V belongs to the image of X, then V, remember, which is a vector of capital V2, must be of the form capital X acting on V prime for some V prime which belongs to capital V1. This, of course, is what it means when we say V belongs to the image of X. Now, what happens when Ti2 acts on V? Ti2 acting on V is, of course, the same as Ti2 acting on XV prime. But since Ti2x is the same as XTi1, again, remember, that was the basic supposition in the lemma. What we have is that this is the same as XTi1 V prime. Now, Ti1 V prime has to be a vector in capital V1. So, X acting on that must give you a result which is in the image of capital X. So, the conclusion is, if you give me any vector V in the image of X, then Ti2 acting on V is also in the image of X for each and every one of the i's from 1 all the way to n. And hence, the image of capital X is also invariant under the action of Ti2, where I runs from 1 all the way up to n. Once again, remember, we had assumed that Ti2s are an irreducible set of operators acting on the space V2, and thus the only possibility for image of X is that either image of X is a singleton set with just the null vector, of course in this case the null vector of V2, or it is all of V2. Now the case where image of X is just the null vector of V2 has already been covered, because this is exactly the same as the kernel of X being all of V1. And if that is the case, then of course capital X is 0. As you have already seen, otherwise X is already known to be 1-to-1. But since image of X now has to be V2, if it's not just the null vector, X is thus onto as well as 1-to-1, and hence X is a bijection and it is invertible. This completes the proof of Schur's first lemma. Schur's second lemma is actually something of a corollary to the first lemma. Remember, the second lemma talks about a single vector space capital V on which you have a bunch of operators which form an irreducible set T1, T2, T3 up to Tn, and we have a map X which commutes with each and every one of these Ti's. What the second lemma says is that this X, the operator which commutes with every one of an irreducible set of operators, has to be a multiple of the identity. To prove this, let us start with an auxiliary linear operator x mu, where x mu is defined to be x minus mu times the identity. Here the identity is, of course, the identity operator acting on the space capital V. Now it's obvious that the identity operator commutes with every operator acting on that space, and hence x mu, just like x, commutes with each one of the Ti's which form our irreducible set of operators. So x mu Ti is the same as Ti x mu. This means that just like capital X, x mu also satisfies all the conditions for Schur's first lemma. Just to remind you, Schur's first lemma can be used in the case when V1 and V2 are both equal to V, the same vector space, and that is exactly the case that we are using here. And according to Schur's first lemma, x mu must then either be 0 or be invertible. Now the statement is true for all values of mu. But let us now think of a special value. Remember that every linear operator on a vector space V has to have at least one eigenvalue. And let this one eigenvalue or one of many eigenvalues be lambda. So if lambda is an eigenvalue of x with a corresponding eigenvector V, then it automatically follows that x lambda V, which of course is x minus lambda times the identity acting on V, must be xv minus lambda V, and since xv is lambda V, lambda being the corresponding eigenvalue, you must get 0. Hence, x lambda is an operator which has a non-zero vector V in its kernel. In other words, it should be impossible to invert x lambda, because if you could invert x lambda, then the equation x lambda V equal to 0 would have immediately led to V equals x lambda inverse acting on 0, and hence to V being 0. Since an eigenvector V is of course a non-null vector, x lambda must be non-invertible. This argument, of course, should be a familiar one to all of you, because this is precisely the argument that leads to the characteristic equation for a matrix when you are trying to find out its eigenvalues. In a more linear algebra-like language, what we are saying is that the eigenvector V belongs to the kernel of x lambda, and that means that the kernel of x lambda is non-empty, and hence x lambda is not invertible. This, of course, is exactly the same thing as what I said right now, except that it's a more linear algebra kind of language. Now we know that for all mu, x mu must be either 0 or invertible, and right now we have proven that if lambda is an eigenvalue of x, then x lambda cannot be invertible. Hence the only possibility is x lambda must be 0, and thus x must be lambda times the identity operator. And this concludes the proof of Schur's second lemma, which essentially says that any operator x which commutes with all the operators in an irreducible set of operators must be a multiple of the identity. Just to remind you once again, x equal to 0 is also a possibility, but if x is 0, then it is a multiple of the identity. So that's also covered within this case. Now that we have stated and proven the two Schur lemmas, let me give you a very simple application which will show you the power of these lemmas. Of course, I have given these lemmas a huge build-up and told you that they will lead us to the wonderful orthogonality theorem, or what is more commonly called the great orthogonality theorem, but that is going to be a topic of the next lecture. Let me just finish this lecture with a very straightforward application, and this application is about abelian groups. The theorem that I am trying to prove here is that all irreducible representations of an abelian group are one-dimensional. So for an abelian group, irreducible representations must be one-dimensional. You cannot have a multi-dimensional irreducible representation of a group if the group happens to be abelian. The proof of this goes as follows. You start with L being an irrep or irreducible representation of an abelian group capital G on some vector space capital V. Then for any given small g belonging to capital G, we have small g g prime equals g prime g for all g prime belonging to capital G. That of course is a basic characteristic of the group being abelian. All the products commute. But because L is a homomorphism, this immediately leads us to LG prime being the same as LG prime LG. But note that what we are saying now is that if you take all the LG primes together, since L is an irreducible representation of the group capital G, then the LG primes together is an irreducible set of operators on the vector space V, and our specific LG commutes with each and every one of this irreducible set of operators. And this immediately tells us that LG must be a multiple of the identity. And this works for every small g belonging to capital G. This is, of course, Schur's second lemma in action. Now, what this tells you is that each and every one of the operators LG are multiples of the identity with possibly different factors. But this automatically also implies that every one-dimensional subspace of capital V is invariant under all of the LGs. Why? Every vector of capital V spans a one-dimensional subspace. You apply LG on that for each of the LGs, you get a multiple of that vector. That means you stay within that one-dimensional subspace. We already said that L is an irreducible representation. If you have an irreducible representation, then you cannot have a non-trivial subspace. But here we see that every one-dimensional subspace of V is invariant. And that seems to be a contradiction, except in one case. The only possibility which will not lead to a contradiction is that L must be acting on a one-dimensional subspace already. That is, V must be one-dimensional, which is why the one-dimensional subspace of V is the whole space, and hence we do not have a non-trivial invariant subspace. And thus, what we have shown is that you cannot have an irreducible representation of an abelian group if your space has dimension more than 1. This, of course, does not say that you cannot have a representation of an abelian group in multiple dimensions. It just says that such representations will always be reducible ones. Now, this particular theorem happens to be very, very important and has quite far-reaching applications in mathematics as well as in physics. But this actually will fade in comparison with the power of the great orthogonality theorem, which we are going to prove using Schur's lemmas in the next lecture. Until then, goodbye.